Welcome to the New Thinking for a New World podcast, where we explore the most pressing issues that are challenging and changing our societies. We are looking for new thinking and new solutions wherever we can find them. Listen as host Alan Stoga, the Talberg Foundation's chairman, challenges his guests for analysis, ideas and actions. Together, we can help make our world at least a bit better.
Today, we share this planet with almost 8 billion people, a number projected to increase to 10 billion by 2050. Already, at least 1 in every 9 of those people are undernourished. And as climate change reduces ag yields and supplies and supply chains are disrupted as they have been by the Ukraine war this year, the specter of large-scale famine seems likely to increase. Maybe Robert Malthus, who in the 18th century insisted that population growth would inevitably outstrip global farming capacity, will finally be proven right. My guest today, David Kaplan, is on a mission to do the opposite, to finally and definitively prove Malthus wrong. David is a global leader in the new field of cellular agriculture, a professor of engineering and chair of the Department of Biomedical Engineering at Tufts University. He wants to feed the world. Welcome, David.
Thank you very much, Alan.
We call this podcast series New Thinking for a New World, and I cannot think of a better example of new thinking, and indeed the kind of new thinking we desperately need, than what you are doing in your laboratory, both in theory and in practice. So let's start at the beginning. What is cellular agriculture, and why do we need it?
I think the easiest way to describe this new technology is essentially growing animals, but without the animals. So really, we're just using the cells that make up animal food, but we don't need to grow farm animals or anything like that. So the idea is really to use the technology that we call tissue engineering. So taking the right cells from the right species in the right environment under the right conditions to get those cells to grow into larger scale tissues that become food of the future. And this term cellular agriculture or cultivated meat is really that approach. So you never need all the other parts of the animal. You never need to grow animals again. You would just use the cells as the origins of those tissues to drive the process.
You told me once that we're not talking about Impossible Burgers or tofu hot dogs, but rather that you're aiming to grow meat, fish, from cells that have the complexity, taste, appearance of, air quotes, real food, so that the consumer would not know whether this hamburger, this steak, this pork chop came from a pasture or from a laboratory. Is that fair?
That's very fair. If we do our job really well, many aspects of this technology would be essentially taste, look, feel the same as currently, animal-grown meat. Although there are parts of the technology being pursued in other parts of the world where you're looking to make foods that don't exist today as well. But the idea, yes, is to emulate what you would already buy and consume at the supermarket or elsewhere, but yet it would be grown from cells without the animal.
So that's the objective, that the person sitting at the McDonald's of the future, or rather perhaps the steakhouse of the future, wouldn't know where this came from. A moment ago, you used the word real, I think, 4 times. So is this real? Is this possible? And more generally, what would the production process look like? We know where it ends up. It ends up with the steak on my plate. Where does it start? And what are in layman's terms, please, what is the process to get us from hither to yon?
So to your first point, is it real? It's absolutely real. I mean, even our own lab, over 20 some odd years, we've been growing human tissues this way, not at scale, but certainly growing tissues of all kinds for the field of regenerative medicine, right? To fix and repair tissues in the human body to understand disease. The idea is now to translate those techniques over to growing food, so non-human derived cells, animal cells of different sorts, to generate these foods. And in the lab today, you could look in our lab and find, chunks of fat growing and muscle tissue growing, things like that. So is the technology real? Absolutely. Is the technology ready for prime time? No. There's a huge gap between where we are in research and where we need to get to in scale to have an impact on feeding the population. But there's a tremendous amount of momentum and lots of discoveries ongoing in many labs around the world now, including our own, to drive this process forward. So progress is fantastic. Companies are trying to put out products already, and there's a lot of momentum moving forward.
I want to come back to several of the points you just made, but if you could walk us through the production process from 60,000 feet, that would be helpful.
Great. So, in simplified terms, the idea first is to get hold of the cells you want. So for us, that means taking a biopsy, could be from a cow, could be from a fish, could be from a lobster, whatever the source of food you want to make, you need the cells from that animal. So first we take a small bit of tissue and use that, bring it back to the lab, isolate the stem cells, and then propagate those stem cells into muscle or fat or connective tissue. Once we've done that, then we have to identify the most optimal sort of cocktail of growth factors to get those cells to continue to grow over long periods of time. So that takes some trial and error, some science to figure out what those cells need to grow. And every cell is a little bit different, so you have to tailor that a bit. And then finally, you have to what we call immortalize those cells. So if you had to go back to the source animal every time you grow this food, it would be a losing proposition, right? You want to not have to do that. So to solve that problem, you need cells that become immortalized. And to do that, you can either do that spontaneously. So for example, in our lab, we've done this with fish stem cells, muscle stem cells, to immortalize them. In other cases, you have to use genetic tools to, by design, immortalize the cells. And for example, we've done that recently in bovine muscle satellite stem cells. So the goal of whatever the source cells is to generate immortalized cells. So those become a repository for any lab, any factory to use to have the same starting material, the biological entity, to drive the process. We then need the right substrate, we call that a biomaterial scaffold, onto which these cells are going to grow. For example, for muscle cells, we want to grow them in aligned units so you get good mechanical properties and good muscle tissue formed. In the case of fat, less a requirement there. But the point is you need a substrate that the cells will stick to and grow on to generate the tissue that you need. And that scaffolding has to be edible, safe for human consumption, available in large quantities, and very low cost. And everything I'm talking about so far means driven by cost here. You just have to keep the cost very low to eventually end up with foods you could eat that are going to be competitive with current, livestock grown foods. Once we have the scaffolding, we have the right cells, now it's a matter of scale. So how do you get from a small bit of tissue growing muscle, fat, or a combination to huge quantities? And that's really where one of the biggest challenges is in the technology at present. And many laboratories, including our own, are developing novel ways to scale. Many startup companies are looking at new bioreactor designs, and all this is sort of underway in a number of fronts to try and solve this problem. This is far and above anything you've ever had to deal with in the pharmaceutical production process, for example, for medications. This is a whole nother scale. And so you have to rethink the entire, scale up process engineering to make sure you can do this in a competitive way, but at scale that's going to have an impact in feeding the population. So that's the process. Along the way, you have to worry about what's the nutritional content, how are you going to cook it, all these other parts that come into food that you need to think about during the entire start to finish.
You've used two words in that description that I want to ask about. The first is immortal. Immortal is one of those concepts that either comes out of DC Comics or religion, and in either case, it's not in the real world. You said it en passant, the cells become immortal. And I'm thinking, as you said that, what I immediately thought of was dog breeding. And the problem with dog breeding is that eventually you begin, or people breeding, I suppose, eventually you get bad outcomes and you start over. So can the cells really be immortal? Or how do you prevent permutations occurring during that long immortal period?
Yeah, this is a great question, and absolutely. So immortal can lead to exactly what you're talking about, right? The challenges with gene stability, changes in the cells, and therefore changes in the downstream food production that you see. So one of the strategies is to generate your initial sort of cultivars of these cells, and those are frozen as your starting stock, right? And you basically make a large amount of these cells and freeze them down and distribute them among many labs. And those have to go through safety checks and quality control all the time. And if you see a change, you have to go back in and re-isolate the cells or edit out the changes and so on. So it's not a static process. It's going to be a constant sort of checking on the cells and making sure they're still okay. One of the other really important features of cellular agriculture for food of the future is that, in fact, it's not going to be a single cell. So, for example, let's take our muscle cell. As I mentioned, we've immortalized our bovine, our cow satellite muscle stem cells. Great. We can provide those to anybody. But it's not going to be the only cell we prepare. For example, we've already made cells like that, where we've engineered into those cells additional nutritional factors. Okay, in this case, for example, beta carotene, a antioxidant like you see in carrots. The idea there is you have more stable cells, less prone to changes due to different environmental exposures, and certainly healthier when you consume them. So that's one of probably 1,000 variants we'll eventually make with bovine cells. So it's not going to be a single cell at that point, single cell source. It's going to be a whole family of cells that you can pick and choose depending on the kind of food you want to grow, depending on the population you're going to feed, depending on what the needs are, the local environment, the local nutritional needs, and so on. So that to me is a huge advantage of cell ag, that you can actually tailor or tune the composition of the food in ways that are unavailable completely to livestock grown food.
Which is to say, if I understood what you just said, you can get your steak, potatoes, and carrots all in one in one piece rather than scattered all over your plate, at least theoretically.
And theoretically, absolutely correct. Whether you want to do that or not, that's a separate issue, right? But that's the general gist. But I would say it's more important not only there, but just if you think about preservation of food, storage stability, shelf stability, sitting in someone's kitchen, whatever it's going to be, having food that's more stable right away buys you a lot of benefits, less food waste and so on, healthier food to begin with and the like.
The other word you used was scale. And obviously all of this is absolutely fantastic, but unless it scales, it's only fantastic. The scale challenge, I suspect, is one of the bigger challenges you face. And you described that there's lots of different approaches at the moment. What is it as an engineer, as a scientist, that persuades you that scale will be possible?
Right. So the first response is you're seeing already what I call mesoscale facilities. So companies have already been investing in scale up for their technologies for cultivated meat or cellular agricultural products. You see those already from Just, you see those from Upside Foods and so on. They have built plants, they're building plants to scale from the research and development to a scale that you can actually see products coming. So I think that's the first stage to say progress is happening. The second optimism is you're seeing new companies formed where their entire being is based on the designing the next scale of bioreactor. So they're not just waiting for things; they're already being proactive about it. And these are companies with strong, good technology base. So I'm very optimistic they'll come up with some creative designs to help achieve those goals. And the third is I just look at our own lab and other labs. So you can look around whether there are labs in the UK, here in Boston, elsewhere, where people are already pursuing these ideas. You're seeing, for example, hollow fiber bioreactors being scaled to use toward cultivated meat. In our own lab, we're developing what we call textile-based bioreactors. The point is these are completely different bioreactors than you'd normally see when you're manufacturing pharmaceuticals and things like this. This takes it to another level. Very scalable technologies where you don't have to fight the battle for mass transfer and other things. You can sort of overcome oxygen availability, nutrient availability. So I'm optimistic there that we can make significant progress, over the next couple of years to really have an impact. Time will tell. We're not there yet, but we're moving in the right direction.
You mentioned in passing the company Just, which is a Singaporean-based company, and they already have a product in the market, I think.
Right. They're one of the few that has a product on the market. Keep in mind, it's fairly limited, right? It's just in a couple of high-end restaurants. The cost is very high, but it sort of demonstrates proof of principle, right? It's a cell-based chicken nugget, essentially, that is out there and available for purchase. I think it also illustrates where I believe the first products may come onto the market for cellular agriculture, and they won't be pure cell-based products. You'll see cells integrated into some of these plant-based products as the first hybrid products coming to market. And the reason is cost. You'll see the plant-based are fairly low cost, just reprocessed plant materials, and the cell-based can then provide inputs to those products to improve taste, quality, consumer acceptance, and so on. And that will get this into the market faster. And then slowly you'll see the cell-based grow in importance. You know, the view of the future is you'll go to the supermarket, you'll still see livestock-derived foods, you'll see plant-derived foods, and then you'll see cell-based foods, all of which will be available to the consumer, and they can make their own choice then as to what they want to use.
If you feel that the world lacks global leaders, please help support the Thalberg Foundation programs. Individual donations are being accepted at thalbergfoundation.org/donate. That's TALLBERG foundation.org/donate.
Let's switch for a minute to chicken of the sea. Some 20% of the protein consumed today comes from the sea. The sea is warming. There's fish and other seafood populations are under enormous pressure. I know that you and your colleagues have already invested a lot of time and effort in cultivating fish cells. Does it work the same way?
Very much works the same way with additional challenges. So first you have to get the fish you want to isolate the cells from. And then the hard work is, do you have the right cells and how do you cultivate them? And there's not a lot of good prior literature that you can go to and identify what we call cell markers and culture conditions and so on, upon which you can move forward very quickly. So with fish and things like crustacea, you have to almost start from scratch, and you have to find and identify or design the right components that you need to follow the cells along the process, make sure they're growing well. Are they still muscle cells? Are they still fat cells, and so on? So yes, it's doable. We've done it quite successfully with one species of fish. We have others going. Crustacea also remain a challenge, but there's lots of work going in our lab and other labs to do that as well. And, you know, one editorial note, I think the needs to use cellular agriculture technology for marine species is more acute even than land-based animals, because the marine environment is just going south. And I mean that in a bad way, right? We know there's toxin, microplastics, there's a litany of challenges today. And so you don't know the quality of fish you're eating today anyway. And my guess is a lot of it isn't as healthy as you want. And these species are going away. And so this is urgent to really start to develop these cell-based materials, cell-based foods from marine species. The other thing I just want to mention is if you look at the aquaculture world, so there is a tremendous amount going on in the world growing salmon by aquaculture. But even there, you're still using fish harvested to then feed those fish, right? So we've got to get that cycle out of there and really use cell-based approaches to feed these fish.
I know you're also working with insects. I've eaten locust tacos in Mexico, but I have the impression that's not what you're working on. So insects as an end in themselves, or insects as an input into something based on their architecture, for want of a better word.
Yeah, so we're very motivated to look at insects as a cell source for cellular agriculture, for food of the future. Very simple reasons. Insect cells are incredibly robust and also very, very nutritious. And so if you take away all the parts of the insect you don't want to look at, whether it's the legs and wings and beaks and all that, right, you're left with the cells. The cells, just like you'd see in an animal, livestock, but now it's just coming from an insect. And if you could carry the same process through, the same technology, right, isolate the cells, generate muscle tissue, fat tissue, grow it on substrates, biomaterials, scale it up, you would have incredibly nutritious and useful food, but it comes at a very, very reduced cost compared to mammalian cells. You don't need, fancy serum or growth factors to do this. You don't need tight control of growth conditions, and yet these cells grow beautifully. And so the cost comes down tremendously by using this cell source. The challenge will be consumer acceptance, right? Consumers in westernized world just haven't had the experience of really eating a lot of insects. So it's going to be a bit of a challenge, whereas other parts of the world routinely eat insects. So I think, thinking about consumer strategies and where this technology could start, maybe it's not in the West. Maybe we start elsewhere. And as it becomes more common and cost effective, then we shift to other parts of the world, including the westernized nations. I would add the insect richness in the world is incredible, as many of your audience may know. So thinking of a vast source of cells to generate all kinds of foods of the future, insects are where it's at, right? They're just such a rich source for different kinds of cells, different flavors of cells, different nutrient compositions. We're just at the start of this.
One of the things that I love about your thinking is that it's aimed at consumers actually accepting and using these products, as opposed to many scientists and engineers. They're going to get the right answer, and the consumer will just have to adjust to it. Because if this stuff is not consumed, then it has failed, which is the test clearly that you're working against. Regulation. I would assume that what goes on in your lab is light years ahead of where many regulators are thinking. They don't have experience in the space. And it's not just your lab, but as you pointed out, there's labs all over the world working to some extent in harmony, is my impression, on these challenges. Do the regulators understand what you're doing? And are they helpful, or are they sea anchors to your progress?
So I think, first of all, in the United States, at least, the regulations are coming. In other words, as far as I've understood, the U.S. Department of Agriculture will promulgate some initial regulations by the end of this year, 2022, possibly into 2023. So I know they've had meetings, discussions, what those regulations are going to say. I do not know, but I know they've been working with the cell ag industry startups to try and marry the needs with, to get these products out there. And as far as I understand it, many of the companies trying to develop these products in the U.S. at least are just waiting on the regulations before they'll release their initial products. So I think all that is getting in sync, and I would imagine over the next few months we'll start to see some definitive details on this. The regulations in Singapore and in parts of Europe are far ahead, so that Singapore could release, the first product, as you know. And I know regulations are being developed in China as well. So worldwide, there's all this effort to develop these regulations to guide the industry going forward, because the industry is growing exponentially. The amount of private investment has been truly remarkable. Billions of dollars we're talking about in this industry because of the need, the opportunity, the advances in the technology, and we have no choice. If you want to look at it long term, we've got to do something sooner than later. So that's driven, all the industrial growth. And, the academic side where I sit has been a little bit behind because there hasn't been a lot of available funding. It's slowly starting to change. Thank goodness we've had profits available to help support things along the way. But there's still a long gap between the private sector and the public sector. We need the public to get the word out, to publish peer-reviewed data, to give confidence to consumers that this is real, as you asked earlier. And I think that's starting to happen. And one more point you raised, which I think is remarkable in my years of doing science, and that is there is harmony. I work with colleagues all around the world on cell ag, and we share materials, we share ideas. It's less privatized in the academic side than ever before because people see the need. There's so much opportunity that we're very much more open to what we're doing and sharing. That's whether it's students going back and forth, whether it's protocols, whether it's cells being shared. It's truly remarkable. It's something that is very refreshing and unexpected, but just something we're all very excited about.
In that spirit, do you think the regulators are talking to each other?
I don't have personal insight there, but I have heard from colleagues that, yes, for example, the FDA talks to the USDA about this. Whether they talk to, other countries and their regulators, I don't know, but I would expect that would be the case, but time will tell.
Or at least hope it would be the case.
I certainly would hope so.
Let's touch at least briefly on ethics. You make the obvious case that cellular agriculture is truly sustainable in the real meaning of that word, that it dramatically reduces demands for water, cuts methane production, infinitely more humane when it comes to treating animals by definition. But are there potential ethical traps on the downside? This comes from, you mentioned earlier that some of the technology comes out of the regenerative medicine space where there are ethical problems all over the place. Are there ones in this space that I'm not thinking about and that we should be thinking about?
Well, I think there are a few. The biggest sort of, as we call it, the elephant in the room is GMO or no GMO, right? So genetically modified organisms or not. And preferences to consume foods that are GMO or not change or vary depending on the area of the world you're in, depending on perceptions of the consumers and so on. So from a research academic standpoint, we work on both. In other words, we generate cells and grow our foods in the lab using both GMO cells modified genetically and cells non-modified. We want to make both, and we want to let the consumer decide. I would say from what I've heard from companies, the vast majority of companies are going non-GMO because of the ethical issues surrounding using genetically modified organisms. So what does that mean in the long run? I think that's going to slow down the rate at which this technology will reach the market. It's not going to prevent it, but it will slow it down. I think GMO allows us to go a lot faster and generate a lot healthier, better foods quicker. But both will work, and we'll see how that proceeds, right? The second sort of ethical side I see is, I would call it the broader religious as well as vegetarian side. I don't know how people perceive these foods. Are they vegetarian? Are they vegan? Are they not? If your religion prevents you from eating a certain kind of food, or presently, if you have cells originating from that animal, are you now allowed to eat cellular agriculture grown food and not the animal itself, right? So these are answers I don't have. I think these will be debated heavily as we move forward, and I think everyone will make their own decisions. The point is, I think we want to provide a menu of items, pardon the pun, for the consumer, and let the consumer decide. And they can decide it based on personal issues, ethical issues, religious issues, social issues, and so on. The last point I want to make on ethics, which I think is really important here, is what I call food equity. The food infrastructure today, and I'm not, other than a consumer, I'm not part of it, is now housed in mega businesses, right, where food distribution drives a lot of what we eat and when we eat and so on. And, people talk a lot about food deserts and other issues, which is a real issue today. We see cellular agriculture as, I'll call it the new horizon there, where food equity is essentially readjusted, right? Because this is technology you could generate in your own home, in a rural community, in a city. The scaling and the location becomes generic. You can decide where you want to do it, how large you want to do it, and what the ingredients are going to be. That's transformative, right? And so I think you're going to see a whole new wave of interest in this because you can rethink the whole food distribution process. That as long as you have the cells, which you can buy from the Amazon of the future, right, the food supplier, and you have the right substrates to grow the cells, and those can be locally derived or purchased and shipped, and the right housing to grow them, you're good to go. So I think this opens up tremendous opportunities that people haven't really thought much about yet, but are starting to, about how to really help communities all over the world have access to healthy foods tailored to their needs, to their preferences, whatever it's going to be going forward.
Let me end by going back to Malthus. Historically, every time he has seemed to be right, technology has come along and proven him wrong. And this obviously is the next opportunity, but that's about speed and scale, because 2050 is tomorrow. Is cellular agriculture up to the task of speed and scale now?
I am very confident the technology and what's going on in the world of cell ag is up to the task. And I say that from real conviction. If I just look at the last 3 years, where we were, where the field was 3 years ago to where we are today, the progress is phenomenal on all the challenges we talked about briefly. And so, the number of companies, the investments, the scientific advances, the technological understanding, honestly, in 3 years, it's just remarkable. And so if I project ahead 3 to 5 years, I'm very, very confident. We're not going to feed 2 billion people in 10 years or 5 years, but I think we'll be well on our way to scaling things, bringing costs down, having things on the market you can start to try and eat. They may be the hybrid products at first. That's okay. So again, if I extrapolate from the last few years, yes, I am incredibly optimistic that we're on the right path. Now, where we get to in 3 to 5 years, depending on the state of the world, is another question. But if left to its own, I think we'll see tremendous progress, significant impact, and we'll be able to feel a lot more confident in feeding 10 billion people by 2050 or so.
So maybe we have to call this not the impossible burger, but the possible steak.
I love it. Let's at least say the possible hamburger.
Oh, thank you very much, David. I've learned a lot. My audience has learned a lot. And good luck. We'll come back and have dinner together soon.
Thanks so much, Alan. Real pleasure. Appreciate it.
Thank you for joining us. Please rate our show on Apple Podcast and subscribe. Meanwhile, you can find us on Facebook, Twitter, and Instagram. Or you can subscribe to our newsletter at talbergfoundation.org to learn more about our work. That's TALLBERG foundation.org. Thank you, and we'll be back again next week for another episode of Talberg's New Thinking for a New World. This podcast was brought to you through the generous support of SNF, the Stavros Niarchos Foundation.